Everyone might be familiar with the usage of thermometers. When digital thermometers were not very common, in the earlier version of the thermometers, you might have noticed a bulb of mercury present at the bottom of the thermometer. Have you ever wondered why mercury is used? Mercury is a toxic metal and also expensive. They could have just used water instead. Why did they choose mercury over water, which is cheap, safe, and easily available? The temperature of a material is a measure of the average kinetic energy per atom or molecule of the given material. So, how does the temperature of a material or a system increase? When kinetic energy per atom of the system increases, its temperature also increases. But how does the kinetic energy of the atom increase? Some kind of external energy must be applied to the system to make it happen. This is normally attained by applying heat. Consider an amount of heat delta Q that is applied to a system and raises its temperature from T to T plus delta T. The heat capacity of a substance is defined as the ratio of heat absorbed by the system to the change in its temperature. That is, S is equal to delta Q by delta T. But do 1 kg and 10 kg of the same substance have the same heat capacity? Obviously not. Heat capacity depends on the mass of the given substance and also the temperature of the substance. So in order to define a constant characteristic of a substance which is independent of the quantity, we divide the heat capacity with the mass of the given substance. This quantity S is called the specific heat capacity, which depends on the nature of the material and the temperature at which the heat is applied. Its SI unit is Joule kilogram raised to minus 1 Kelvin raised to minus 1. We can also define heat capacity per mole of a given substance instead of its mass. It is the molar specific heat capacity defined as C is equal to S by mu or 1 by mu times delta Q by delta T. The SI unit of molar specific heat capacity is Joule mole raised to minus 1 Kelvin raised to minus 1. It depends on the nature of the material, temperature, and the conditions under which the heat is applied. We have considered heat as a form of energy and hence it has the SI unit Joule. But during the early 1800s, when the branch of calorimetry was in its developmental stage, a French physicist and chemist named Nicolas Clement introduced the term calorie as a unit of heat energy. 1 calorie is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. With the evolution of instruments that gave more accurate measurements, it was found that the heat required to increase the temperature of water by 1 degree varies with the change in the temperature. This made the then scientific community redefine the term calorie. The new definition of calorie was framed as the heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Later, the mechanical equivalent of heat was defined in terms of work done as the work done to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. This was numerically found to be 4.186 Joule gram raised to minus 1. Since heat is identified as a form of energy, the unit of heat was modified to joules. Hence, the specific heat capacity of water is 4.186 Joule gram raised to minus 1 Kelvin raised to minus 1 or 4186 Joule kilogram raised to minus 1 Kelvin raised to minus 1. This gives us an answer to the question in the beginning. Why is water not used instead of mercury in a thermometer? Water has a very high specific heat capacity, which means it needs a lot of heat to get a unit rise in temperature. The specific heat capacity of mercury is 140 Joule kilogram raised to minus 1 Kelvin raised to minus 1, which is very less compared to that of water, and hence it is best suited for a thermometer. We know that the molar specific heat capacity depends on the conditions under which the heat is applied. For gases, two specific heats are defined. The specific heat capacity at constant pressure is denoted as Cp, and the specific heat capacity at constant volume is denoted by Cv. The relation between Cp and Cv can be derived using the first law of thermodynamics. Here Cp is equal to delta Q by delta T at constant P, and Cv is equal to delta Q by delta T at constant V. According to the first law of thermodynamics, delta Q equal to delta U plus P delta V. Consider that the heat delta Q is absorbed by the given substance to increase the temperature by delta T, and the volume is kept constant. Then delta Q by delta T at V is equal to delta U by delta T at V plus P delta V by delta T at V. But since the volume is kept constant throughout the process, that is delta V equal to 0, and hence the work done term gets vanished. Also, the internal energy is independent of the pressure, so the above relation becomes Cv is equal to delta U by delta T. Now once again consider the first law of thermodynamics. This time consider that a heat delta Q is absorbed by the given substance to increase the temperature by delta T, and the pressure is kept constant. Therefore, delta Q by delta T at P equal to delta U by delta T at P plus P delta V by delta T at P. But the internal energy does not depend on volume. Therefore, the equation becomes delta Q by delta T equals delta U by delta T plus P delta V by delta T. Now, subtracting Cv from Cp, we get Cp minus Cv is equal to P delta V by delta T at constant pressure. Now, for 1 mole of an ideal gas, we have the equation Pv is equal to RT. That is at constant pressure. We can rewrite this equation as P delta V by delta T equals R. Therefore, we get Cp minus Cv is equal to R. Note that this relation holds true only for an ideal gas. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.